November 3rd, 1950. The Chongchon River, North Korea. Captain James Thornton stood on the frozen mud of the riverbank, watching his M26 Pershing tank sink 3 inches into a Bailey bridge deck that had been designed 6 years earlier for tanks weighing 15 tons less. The deck groaned. The pontoons beneath dipped below their safe waterline. Thornton's gunner, Sergeant Paul Medeiros, looked at him through the commander's cupola with an expression that needed no words. They were halfway across a 100-meter span with Chinese artillery zeroing in from the hills, and the bridge was failing beneath them. The mathematics were simple and terrifying. The M26 Pershing weighed 46 tons fully loaded. The Bailey pontoon bridge they were crossing had been engineered in 1941 for the 33-ton Sherman. Every manual, every field calculation, every safety margin had been exceeded before Thornton's tank even touched the approach ramp. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engineers who built this crossing knew it. Thornton knew it. But the alternative was leaving a $70 million tank and a 5-man crew on the wrong side of the river with 2 Chinese divisions closing from the north. The bridge deck flexed again. Thornton could feel it through the tank's suspension, a slow, rhythmic bounce that suggested the pontoons were approaching their critical displacement. Water was now visible above the pontoon rails, lapping at the Bailey panels. Physics didn't care about military necessity. Archimedes' principle, written 22 centuries before anyone built a tank, stated the facts without mercy. An object displaces water equal to its weight. When displacement exceeds buoyancy, the object sinks. The only question was whether they would reach the south bank before that equation resolved itself. The Chongchon River crossing represented a problem that military engineers had been trying to solve since 1945, when the war in Europe ended, and everyone realized the next war would be fought with heavier tanks. The Sherman had defined portable bridge engineering during World War II. At 33 tons, it sat within the comfortable capacity of Bailey bridges and M2 pontoon systems. Engineers could build crossings in hours, move entire armoured divisions across rivers, and rely on equipment that had been tested across every river from the Rhine to the Elbe. But the Sherman was obsolete before the war ended. German Panthers and Tigers had proven that armour thickness mattered. Post-war Soviet tank development emphasized heavy armour and large-caliber guns. The American response was the M26 Pershing, rushed into service in February 1945. At 46 tons, it could stand against German heavy tanks. It could also break every bridge the US Army owned. The British faced the same crisis with their Churchill tank, which topped out at 43 tons, and their engineers were already designing the Centurion, which would eventually exceed 50 tons. The Soviets were even worse off. Their IS-2 heavy tank weighed the same as the Pershing, and intelligence suggested they were developing even heavier designs. Every major military power was building tanks that their own engineers couldn't transport across rivers without permanent bridges or engineering miracles. The problem wasn't just weight. It was weight combined with the tactical requirement for speed. World War II had proven that rapid river crossings determined the pace of offensive operations. The side that could bridge a river in hours controlled the tempo. The side that needed days or weeks to build crossings lost the initiative, gave the enemy time to reinforce, counter-attack, and turn every river into a killing ground. Heavy tanks were useless if they couldn't cross water obstacles faster than the enemy could defend them. Captain Thornton's Pershing cleared the Chongchon River bridge, with 6 inches of freeboard remaining on the pontoons. The Chinese artillery barrage hit the north bank 90 seconds later, destroying the approach ramp and killing 2 engineers who were already setting demolition charges to deny the crossing to Chinese forces. Thornton's tank was the last American armor to cross that bridge. The next day, US engineers would attempt another crossing 15 kilometers downstream, and the same problem would repeat itself. Heavy tanks, light bridges, physics that refused to compromise. The crisis facing military engineers in 1950 wasn't new. It was physics meeting metallurgy, and physics was winning. Every army that emerged from World War II understood that future tanks would be heavier, more armoured, and more lethal. Soviet doctrine, shaped by their experience fighting German Tigers and Panthers, emphasized armor thickness and gun caliber over mobility. American doctrine, scarred by watching Sherman's burn after failing to penetrate German frontal armor, demanded better protection for future designs. British doctrine, refined through 5 years of mechanized warfare across 3 continents, concluded that survivability required weight. The result was a global arms race toward heavier main battle tanks, and nobody had solved the bridge problem. The Bailey Bridge, Donald Bailey's revolutionary design from 1940, remained the gold standard for tactical bridging in 1950. Its modular panel system allowed rapid construction using interchangeable components. A trained engineer company could assemble a Bailey Bridge in hours rather than days. The system had won World War II by keeping Allied armor moving across hundreds of rivers, but the Bailey Bridge had load limits determined by material strength and structural engineering principles that couldn't be ignored. A standard single-panel Bailey Bridge could support approximately 15 tons. Stack 2 panels vertically to create a reinforced truss, and capacity increased to 30 tons. Stack 3 panels, and you reached roughly 40 tons, but there was a hard limit. Bailey panels were made from high-tensile steel with specific material properties. Each panel weighed 270 kilograms. Stack them higher, and the bridge's own weight consumed more of its load capacity. Stack them too high, and the structure became unstable, vulnerable to lateral forces and oscillation. British engineers calculated that a quadruple reinforced Bailey Bridge could theoretically support 55 tons. But that theoretical capacity assumed perfect construction, ideal conditions, and static loading. In combat, with bridges assembled rapidly under artillery fire, with tanks crossing at speed rather than crawling, with wind, current, and structural fatigue all degrading performance, the actual safe load dropped by 15 to 20%. A bridge rated for 55 tons couldn't reliably carry a 50-ton tank. The Americans conducted extensive testing at Fort Belvoir, Virginia, throughout 1946 and 1947, trying to extend Bailey Bridge capacity. They experimented with steel alloys, revised panel geometry, and tested double-deck configurations, where 2 complete bridges were stacked vertically. The results were discouraging. Yes, you could build Bailey bridges capable of carrying 50-ton loads, but those bridges required so many panels, so much assembly time, and so much specialized launching equipment that they lost the rapid deployment advantage that made Bailey bridges tactically valuable. A triple reinforced Bailey bridge capable of carrying a Pershing required approximately 4 times as many panels as a standard Sherman bridge. Assembly time increased from 4 hours to 14 hours. The bridge components weighed so much that engineers needed cranes and specialized vehicles just to position the panels. What had been a tactical bridge, built by infantry engineers with hand tools, became a semi-permanent structure requiring dedicated engineering, battalions and equipment that couldn't keep pace with advancing armor. The French faced this problem during their Indochina operations in the early 1950s. They deployed M24 Chaffee light tanks, which at 18 tons could cross standard Bailey bridges easily. But the Chafees were undergunned and lightly armored, vulnerable to ambush by Viet Minh forces using recoilless rifles and anti-tank mines. The French needed heavier tanks for firepower and protection. They also needed bridges that could carry those tanks through terrain where every river became a choke point. They never solved the equation. French armor remained limited to light tanks throughout the Indochina War, sacrificing firepower and protection for mobility. Soviet engineers approached the problem differently. Rather than trying to make bridges stronger, they tried to make tanks lighter in specific situations. The T-54 medium tank, which entered service in 1949, weighed 36 tons, similar to a Sherman. Soviet designers achieved this through aggressive weight optimization, thin armor on the bottom and rear, where enemy fire was less likely, a compact 3-man crew instead of 4 or 5. Minimal ammunition storage. The T-54 could cross improved Bailey bridges without exceeding capacity, but the Soviets also recognized they needed heavier tanks for breakthrough operations. The IS-3 heavy tank, unveiled publicly in the Berlin Victory Parade of 1945, weighed 46 tons, and mounted a 122mm gun. It was designed to smash through fortified defenses. It was also too heavy for most tactical bridges. Soviet doctrine accepted this limitation by treating heavy tanks as breakthrough weapons rather than exploitation forces. Heavy tanks would cross rivers using prepared engineering sites with permanent or semi-permanent bridges. Light and medium tanks would conduct rapid advances using tactical bridges. Western intelligence observed this Soviet doctrine and drew conclusions that shaped NATO planning for the next 40 years. If war came in Europe, Soviet heavy armor would concentrate at prepared crossing sites. Those sites would become choke points, vulnerable to airstrikes and artillery. Meanwhile, Soviet light armor would exploit tactical bridges, but lack the firepower to defeat Western defensive positions. The doctrine seemed workable until intelligence reports in 1953 revealed that the Soviets were developing a new generation of main battle tanks that combined the firepower of heavy tanks with weights under 40 tons. The T-55, which entered service in 1958, weighed 36 tons, but mounted a 100mm gun nearly as powerful as the IS-3's 122mm weapon. Soviet engineers had solved the weight problem through superior metallurgy and design efficiency. The Americans and British suddenly faced a crisis. Soviet tanks could cross tactical bridges while maintaining near-heavy tank firepower. Western tanks were trapped in a choice between mobility and protection. The American response was the M48 Patton, which entered service in 1952. At 47 tons, it exceeded Bailey Bridge capacity unless engineers built reinforced structures. The British developed the Centurion Mark III, which also pushed past 45 tons. Both tanks offered excellent protection and firepower. Both tanks also created a logistics nightmare for engineer battalions trying to keep armoured divisions moving across rivers. NATO war games in 1954 through 1956 repeatedly demonstrated the problem. Soviet armour could cross rivers using standard tactical bridges and maintain offensive tempo. NATO armour required extensive engineer preparation at every crossing, slowing advance rates and creating predictable choke points where Soviet aircraft and artillery could inflict devastating losses. The side with lighter tanks controlled the pace of battle. The side with heavier tanks had better survivability in direct combat, but couldn't maneuver fast enough to exploit tactical advantages. British engineers at the Military Engineering Experimental Establishment began exploring radical solutions in 1954. What if the bridge didn't support the tank at all? What if the tank crossed underwater, using its own engines and sealed crew compartments? The concept, called deep wading, required extensive modifications, air intake snorkels extending above water level, waterproofed electrical systems, sealed hatches with pressure testing, exhaust systems that could operate while submerged. The engineering was complex, but theoretically possible. The British tested deep wading with Centurion tanks in 1955. A Centurion, fully waterproofed with a snorkel system, could cross rivers up to 4 meters deep at walking pace. The technique worked, but had severe limitations. Soft-bottom rivers caused tanks to bog down in mud. Fast currents could push tanks off course or flip them entirely. Crew members inside sealed tanks couldn't escape if something went wrong, which meant deep wading carried catastrophic risks if the tank lost power or struck an obstacle. Most critically, deep wading required hours of preparation time to install snorkels and waterproofing before each crossing, then more hours to remove the equipment afterward. Deep wading solved the bridge weight problem by eliminating the bridge, but it introduced new problems that were equally difficult. NATO exercises using deep wading showed that armoured units needed 6 to 8 hours to cross a major river, compared to 2 to 3 hours using bridges. The technique was useful in specific situations, but couldn't replace tactical bridges as the primary crossing method. The Americans explored a different approach. What if bridges could be stronger without being heavier? Material science offered potential solutions. Aluminum, alloys, still relatively new in structural applications, offered strength-to-weight ratios superior to steel. A bridge panel made from aluminum could be 40% lighter than steel while maintaining the same load capacity. Lighter panels meant engineers could build reinforced bridges without increasing the total weight that needed to be transported and assembled. The U.S. Army Corps of Engineers contracted with the Reynolds Metals Company in 1955 to develop aluminum Bailey-style panels. The technical challenges were significant. Aluminum was more expensive than steel, which mattered for mass production. Aluminum welding required different techniques than steel, which complicated manufacturing. Most importantly, aluminum's fatigue characteristics differed from steel. Steel panels could be stressed repeatedly and maintain their strength. Aluminum panels developed microscopic cracks after repeated stress cycles, eventually leading to catastrophic failure. The test program at Fort Belvoir revealed these problems through painful trial and error. In December 1956, an aluminum test bridge collapsed while carrying an M48 pattern during cold weather trials. The inquiry determined that aluminum's brittleness at low temperatures, combined with fatigue from previous load cycles, had caused 3 panels to fail simultaneously. The bridge dropped the 47-ton tank into the Potomac River. All 5 crew members escaped, but the incident ended aluminum bridge development for another decade. Engineers were left with steel Bailey panels that couldn't reliably carry 50-ton tanks, deep wading that required too much preparation time, and aluminum that failed unpredictably. The bridge problem remained unsolved, as tensions between NATO and the Warsaw Pact escalated throughout the late 1950s. August 13, 1961. The Berlin Wall rose overnight, turning Cold War tensions into a very physical barrier. Western intelligence analysts noted that Soviet forces in East Germany included 16 tank divisions, equipped primarily with T-54 and T-55 medium tanks. Those tanks, at 36 tons, could cross any bridge Soviet engineers could build. NATO's heavy tanks, concentrated in West Germany, weighed 10 tons more and required specialized crossings. The operational implications were clear. If war came, Soviet armor would have a mobility advantage at every river crossing. The Rhine, the Weser, the Elbe, every major water obstacle in Central Europe would become a race between NATO engineers trying to build heavy bridges and Soviet tanks exploiting their weight advantage. NATO would be forced to defend at rivers rather than conducting mobile operations, surrendering the initiative to an enemy that could move faster across the same terrain. British military planners, studying this problem, concluded that NATO needed a revolutionary bridge design that could be deployed in minutes rather than hours and carry 60-ton loads to future-proof against even heavier tank development. The requirement seemed impossible. Physics dictated that stronger bridges required more material. More material meant more weight. More weight meant slower deployment. Every attempt to optimize one factor made the others worse. The breakthrough came from an unexpected direction. In 1961, a British civil engineer named Peter Mabey was working on modular construction systems for commercial buildings. Mabey's insight was similar to Donald Bailey's 20 years earlier. Instead of making bridge components stronger through thicker materials, make them more efficient through better geometry. A triangular truss distributes load more efficiently than a rectangular frame. A curved arch transfers weight to abutments better than a flat span. The mathematics of structural engineering had been understood for centuries. Mabey's innovation was applying those principles to mass-produced modular components that could be assembled rapidly in field conditions. The Mabey-Johnson bridge system, developed between 1961 and 1963, used panels that were lighter than Bailey panels but achieved higher load capacity through optimized geometry. Each panel incorporated a curved top chord that created a slight arch when multiple panels were connected. This arch effect distributed weight more evenly across the structure. The panels also used a hexagonal lattice rather than Bailey's rectangular pattern, which provided greater resistance to lateral forces while using less steel. British Army trials in 1963 demonstrated that a Mabey-Johnson bridge could carry a 55-ton load using 30% fewer panels than an equivalent Bailey bridge. More importantly, the Mabey system could be assembled faster because each panel was lighter and easier to handle. A standard Bailey panel required 6 men to carry. A maybe panel needed only 4. That difference translated to significantly faster assembly times when building large structures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But even the Maybe system couldn't reach 60-ton capacity without becoming too heavy for rapid deployment. The fundamental problem remained. Steel bridges strong enough to carry the heaviest tanks were too massive to build quickly. Something had to change, and that change came from recognizing that the bridge didn't need to carry the entire load at once. The concept of load distribution through multiple vehicles had been explored theoretically since the 1920s, but practical applications remained elusive. The idea was straightforward. Instead of building one enormously strong bridge, build a lighter bridge and ensure that only one tank crosses at a time, with sufficient spacing to prevent load concentration. Control the traffic, and you control the structural demands. NATO engineering doctrine was revised in 1964 to include precise traffic control protocols for heavy bridges. Engineers, with stopwatches, stood at bridge entrances. Each tank was released only after the previous tank had cleared the far side. For a 60-ton tank crossing a 200-meter bridge, minimum spacing was calculated at 90 seconds. This prevented 2 heavy tanks from simultaneously loading the bridge structure, effectively cutting peak loads in half. The traffic control solution worked, but it created a new bottleneck. An armored battalion with 54 tanks needed 81 minutes to cross a single bridge using optimal spacing. Add in command vehicles, supply trucks, and supporting elements, and a single armored battalion required nearly 3 hours to complete a crossing. An armored division with 3 tank battalions needed 9 hours. In a fluid combat situation where Soviet forces could be minutes behind advancing NATO units, 9 hours at a single crossing point was tactically unacceptable. The American solution emerged from research at the Army Mobility Equipment Research and Development Center in Fort Belvoir. Instead of making bridges strong enough for any tank, make bridges quickly adjustable for different weight classes. The medium girder bridge system, developed between 1965 and 1968, used aluminum components that could be configured in multiple arrangements depending on required load capacity. For light vehicles up to 30 tons, engineers built a single-truss MGM bridge that could be assembled in 30 minutes. For medium tanks up to 45 tons, they added reinforcing girders that clipped onto the basic structure, doubling capacity in 20 additional minutes. For heavy tanks approaching 60 tons, they built a double-deck configuration where 2 complete bridges were stacked vertically and connected with cross-bracing. The MGB system's genius was its modularity at multiple levels. Not only were individual components interchangeable, but entire configuration levels could be added or removed based on tactical requirements. If engineers expected only light vehicles, they built a light bridge and saved time. If heavy armor arrived unexpectedly, they could reinforce the existing structure rather than starting over. The system reduced the planning burden on engineer commanders, who often didn't know what equipment would need to cross until units were already queued at the riverbank. Testing at Fort Hood, Texas, in 1968 showed that a combat engineer company could build a 60-ton capacity MGB bridge across a 100-meter gap in 90 minutes. That was still longer than Bailey Bridge construction for lighter loads, but it was faster than any previous method for heavy tank crossings. More importantly, the MGB bridge was lighter overall than equivalent Bailey structures, which meant engineers could carry more bridge capacity on the same number of trucks. The Soviets were not idle during this period. Western intelligence received fragmentary reports of Soviet bridge development throughout the 1960s, but the full scope of their program remained classified until much later. What NATO planners didn't realize was that Soviet engineers had solved the heavy tank bridge problem through a completely different approach. Instead of building better stationary bridges, they developed mobile bridges that tanks could carry and deploy themselves. The MTU-55 bridge layer, which entered service with Soviet forces in 1965, was built on a T-55 tank chassis. It carried a folding scissors bridge that could be deployed across gaps up to 18 meters in 3 minutes. The bridge could support tanks up to 50 tons, which covered every vehicle in the Soviet inventory at that time. More importantly, the bridge layer kept pace with advancing armor, arriving at obstacles simultaneously with the tanks that needed to cross rather than requiring engineers to move forward separately. NATO forces had bridge layers as well. The British Centurion AVRE could deploy a 30-meter bridge. The American M60 AVLB carried a similar system, but Soviet doctrine integrated bridge layers more thoroughly into armored formations. Each Soviet tank regiment included a dedicated bridge layer platoon that trained constantly with the tanks they supported. Western bridge layers were typically concentrated in engineering battalions, which meant they had to be requested, dispatched, and directed to specific crossing sites. The organizational difference meant Soviet units could respond to river obstacles minutes faster than NATO equivalents. British exercises in 1969 revealed this doctrinal vulnerability. When armoured regiments encountered unexpected water obstacles during manoeuvres, the average time from obstacle identification to first tank crossing was 47 minutes for Soviet-style organizations compared to 93 minutes for NATO organizations. That 46-minute difference was tactically decisive. In mechanized warfare, 46 minutes allowed defenders to establish anti-tank positions, call in artillery support, and prepare ambushes that could destroy entire formations at choke points. The NATO response was organizational rather than technological. Engineering doctrine was revised in 1970 to push bridge layers forward into direct support of armoured regiments rather than holding them in battalion reserve. British armoured divisions received additional bridge layer squadrons. American armoured cavalry regiments added bridge layer vehicles to their organic equipment. The goal was matching Soviet response times through better organization rather than superior equipment. But bridge layers had a fundamental limitation. They worked for gaps up to 30 meters. Most rivers in Central Europe were wider. The Rhine measured 200 to 400 meters across, depending on location. The Elbe ranged from 150 to 300 meters. These major rivers required ribbon bridges, floating structures, that could stretch across any width, but took hours to deploy and were vulnerable to current, weather, and enemy fire. The U.S. Army's Mobile Assault Bridge System, introduced in 1971, attempted to solve this problem through mechanization. Instead of engineers hand-assembling pontoon bridges, specialized vehicles carried folding bridge sections that deployed hydraulically. The MAB system could theoretically construct a 200-meter floating bridge in 90 minutes using 8 bridge vehicles working simultaneously. Field trials revealed problems immediately. The MAB vehicles were based on M113 armoured personnel carrier chassis, which were tracked but lightly armoured. Moving them to bridge sites under fire meant accepting losses. Each vehicle carried one bridge section weighing approximately 8 tons. If one vehicle was destroyed or broke down, the entire bridge was incomplete. The system required precise coordination between 8 separate vehicles launching their sections simultaneously. In training conditions with experienced crews, coordination was difficult. In combat conditions with inexperienced replacement crews under artillery fire, coordination often failed completely. Soviet observers noted NATO's struggles with mobile bridging and developed their own system with characteristic Russian emphasis on simplicity and redundancy. The PMP floating bridge, introduced in 1970, consisted of individual motorized pontoon sections that drove into the water under their own power, connected to form a continuous floating roadway. Each pontoon was a boat with wheels, driven to the water's edge by its own motor, then propelled across the river by the same engine. The genius of the PMP system was its independence. Each pontoon operated autonomously. If one was destroyed, the remaining pontoons continued functioning, and engineers simply filled the gap with a spare section. The system required no special launching equipment, no complex coordination between multiple vehicles. Engineer crews drove the pontoons to the river, steered them into position, and locked them together using simple mechanical clamps. Western intelligence acquired detailed information about the PMP system in 1973 when Egyptian engineers used Soviet-supplied equipment to cross the Suez Canal during the Yom Kippur War. Egyptian forces deployed multiple PMP bridges across the canal in under 4 hours, while under Israeli artillery fire, allowing armor to establish bridgeheads that Israeli forces couldn't contain. The speed and simplicity of the PMP system demonstrated that Soviet engineers had solved problems NATO was still struggling with. American engineers analyzed captured PMP sections and concluded the Soviet design was less sophisticated than NATO systems, but more reliable under combat conditions. American bridges used complex hydraulic systems and precision mechanical components. Soviet bridges used simple motors, basic mechanical linkages, and components that could be repaired with improvised materials. The American approach assumed trained maintenance crews and supply chains would keep equipment operational. The Soviet approach assumed equipment would be used by minimally trained conscripts who had no spare parts and needed to improvise repairs under fire. The realization forced NATO to reconsider their entire approach to tactical bridging. Superior technology meant nothing if it was too complex to use under combat stress. The armies that won battles weren't always those with the best equipment, but those whose equipment actually worked when everything else was chaos. The 1970s saw NATO engineering doctrine caught between two competing philosophies. American doctrine emphasized technological solutions. Stronger materials, better designs, more sophisticated deployment systems. European doctrine, particularly British and West German, emphasized organizational solutions. Better training, clearer procedures, more engineer units distributed forward with combat formations. Both approaches had merit. Neither had fully solved the heavy tank bridge problem. The challenge intensified in 1973 when the American M60A1 Patton, the standard U.S. main battle tank, was upgraded with additional armor, bringing its weight to 52 tons. British Chieftain tanks, introduced to British Army of the Rhine units, weighed 55 tons. Soviet T-62 tanks remained at 36 tons, giving Soviet forces a continuing mobility advantage at tactical river crossings. NATO's technological edge in armor protection and fire control was being negated by the simple fact that Soviet tanks could cross bridges faster. The crisis reached its peak during the Reforger exercises of 1976. Reforger, short for Return of Forces to Germany, was NATO's annual demonstration of their ability to reinforce European forces rapidly in the event of Warsaw Pact invasion. The 1976 exercise, called Reforger 76, involved moving an entire American armored division from ports in the Netherlands to defensive positions in West Germany, crossing multiple rivers along the way. The exercise exposed catastrophic weaknesses in NATO bridging capacity. At the Weser River, engineers required 11 hours to establish crossings capable of handling the division's M60 tanks. During those 11 hours, the division was completely vulnerable, strung out along approach roads with no ability to maneuver. Evaluators noted that if this had been actual combat, Soviet aircraft and artillery would have destroyed the division while it waited for bridges. The embarrassment was compounded when Warsaw Pact observers, invited as part of confidence-building measures, watched the entire debacle and undoubtedly reported every detail to Moscow. American engineers blamed inadequate equipment and insufficient bridge inventory. European NATO members blamed poor American doctrine and lack of training. Both were partially correct. The real problem was that NATO had been incrementally improving World War II-era bridging systems while tank weights had doubled. Engineers were trying to solve a 1970s problem with 1940s technology, and no amount of training or doctrine could overcome the fundamental physics. The American response was the improved ribbon bridge system, development of which began in earnest in 1977. The IRB was conceived as a complete replacement for every tactical bridging system the U.S. Army operated. It needed to carry 60-ton vehicles, deploy in under 2 hours, function in high-current conditions, and be simple enough that minimally trained crews could operate it under combat stress. The engineering team at the Army Engineer Waterways Experiment Station in Vicksburg, Mississippi, approached the problem by studying every successful military bridge from the previous 3 decades. They analyzed Soviet PMP systems, British medium girder bridges, and American floating ribbon bridges. They examined failure reports from combat operations in Vietnam, where monsoon currents had destroyed numerous tactical bridges. They reviewed maintenance records to identify which components failed most frequently and why. The IRB design that emerged in 1978 represented a synthesis of 30 years of hard-won lessons. Each bridge bay section measured 6.7 meters long and 2.1 meters high, constructed from welded aluminum for optimal strength-to-weight ratio. The bay sections were hollow, providing buoyancy without requiring separate pontoons. Each section displaced enough water to support 7.5 tons, and sections could be connected side by side or end to end to create bridges of any required length or load capacity. The revolutionary aspect was the ramp bay sections, specialized components that could be adjusted hydraulically to match different bank heights. Previous bridge systems required extensive site preparation to level approaches. The IRB could adapt to uneven terrain, reducing preparation time from hours to minutes. Engineers could arrive at a river, assess the banks, and begin bridge construction immediately without bulldozing approach ramps. Load capacity was achieved through an innovative interior structure. Each bay section contained a Warren truss, a triangular lattice that distributed weight evenly across the entire section. The mathematics were elegant. A single bay section could support 7.5 tons, connect two sections side by side, and capacity increased to 15 tons. Connect four sections in a 2x2 configuration, and capacity reached 30 tons. For the heaviest vehicles, engineers configured sections in a 3x3 grid, achieving load capacity exceeding 65 tons with built-in safety margins. The U.S. Army conducted proof-of-concept tests at Fort Story, Virginia, in 1979. Engineers built a test bridge across the Chesapeake Bay using pre-production IRB sections. The bridge measured 130 meters, required 20 bay sections, and was constructed in 73 minutes by a single engineer company. An M60A1 tank weighing 52 tons crossed successfully with pontoons showing less than half their maximum safe displacement. The test was considered successful, though engineers noted that calm water conditions and trained crews weren't representative of combat scenarios. Combat scenario testing began in 1980 at Fort Lewis, Washington, where engineers simulated high-stress conditions. They constructed IRB bridges at night, under simulated artillery fire with smoke obscuring visibility, and with crew members wearing full chemical protective gear. The results were mixed. Under optimal conditions, experienced crews built IRB bridges quickly and reliably. Under degraded conditions with stress and limited visibility, assembly times doubled and error rates increased significantly. The errors were instructive. The IRB system used hydraulic connectors that locked bay sections together. In darkness or smoke, crews sometimes misaligned the connectors, requiring sections to be disconnected and repositioned. This wasn't a design flaw so much as a training issue. Crews needed more practice working in degraded conditions until section alignment became automatic rather than requiring visual confirmation. The Army revised training protocols to emphasize night construction and chemical environment operations. Meanwhile, the M1 Abrams tank was entering production, and it presented a new challenge. Early production M1S weighed 54 tons, within IRB capacity. But the Army was already planning armor upgrades that would add reactive armor tiles, improved protection packages, and heavier armament. Projections suggested that fully upgraded M1A1 variants would approach 60 tons, consuming almost all safety margins in IRB design. British engineers faced an even worse situation. Their Challenger tank, entering service in 1983, weighed 62 tons in combat configuration. This exceeded the capacity of every tactical bridge system NATO operated, including the IRB, which wasn't yet in full production. British doctrine was forced to classify the Challenger as a heavy tank requiring specialized crossing equipment rather than a main battle tank capable of rapid deployment. The solution that emerged was a return to World War II principles, specifically the lesson that traffic control could substitute for structural strength. British engineers developed the heavy crossing doctrine, formalized in 1984, which specified precise procedures for moving 60-ton-plus vehicles across tactical bridges. The doctrine required engineer controllers at both bridge entrances with radio communication. Only one heavy tank was allowed on the bridge at any time. The tank crossed at walking speed, approximately 4 kilometers per hour, to minimize dynamic loading. Engineers monitored bridge deflection using visual markers. If deflection exceeded calculated safety limits, crossing operations halted until structural analysis could be completed. The heavy crossing doctrine worked, but it was excruciatingly slow. A Challenger tank needed approximately 4 minutes to cross a 200-meter bridge at walking speed. A British armoured regiment with 56 Challengers required nearly 4 hours to complete a crossing using a single bridge, and that assumed perfect conditions with no breakdowns, no enemy interference, and no gaps in the crossing sequence. In practical terms, the doctrine meant British heavy armour couldn't conduct rapid manoeuvre warfare. They could defend positions effectively, but offensive operations were constrained by bridge capacity at every river obstacle. The Americans addressed this through redundancy rather than individual bridge capacity. U.S. doctrine specified that engineer battalions supporting armoured divisions should be capable of simultaneously operating multiple crossing sites. Where the British built one heavy bridge and crossed slowly, the Americans built 3 medium bridges and crossed simultaneously. The mathematical result was similar. Both approaches moved an armoured regiment across a river in approximately 4 hours, but the American method distributed vulnerability across multiple sites, rather than concentrating all forces at a single choke point. Soviet doctrine, observed through intelligence collection and analysis of Warsaw Pact exercises, took yet another approach. They accepted that their tanks were lighter than NATO equivalents and built their operational plans around that mobility advantage. Soviet crossing doctrine emphasized speed over sophistication. They would attempt multiple crossings simultaneously, using simple equipment, accepting higher losses at individual sites in exchange for overwhelming defenders through sheer number of penetrations. KGB reports acquired by Western intelligence in the 1980s revealed that Soviet planners calculated NATO forces could defend 3 to 4 major crossing sites along any river line with available artillery and air power. Therefore, Soviet doctrine called for attempting 8 to 10 crossings simultaneously across a broad front. NATO would destroy half of them, but the remaining 4 or 5 successful crossings would be sufficient to establish bridgeheads and continue the offensive. The math was brutal but logical. Soviet planners assumed they would lose entire engineer battalions and their equipment at failed crossings. They had accepted that cost as the price of maintaining offensive tempo. NATO planners found this doctrine deeply troubling because it suggested the Soviets had solved the mobility problem through willingness to accept casualties that Western democracies would find politically unacceptable. A Soviet motor rifle division losing 200 engineers and 20 bridge sections while forcing a river crossing would be considered a success if it enabled the division to advance. An American division suffering similar losses would face congressional investigations and demands for revised doctrine. The ideological difference manifested in equipment design. The IRB system that entered full production in 1984 was engineered for crew safety and equipment preservation. Bay sections included ballistic protection for crew members operating hydraulic systems. Connection mechanisms were designed to prevent accidental separation, even if damaged by artillery fragments. The system cost approximately $3.2 million per complete bridge set, which made it too expensive to treat as expendable. The Soviet PMP system, by contrast, was designed for rapid replacement rather than durability. Individual pontoon sections cost approximately 1/10 the price of equivalent NATO components. Soviet doctrine assumed pontoons would be damaged or destroyed regularly and planned replacement pipelines accordingly. Quality control was looser, maintenance standards were lower, but production rates were higher. The Soviets could replace combat losses faster than NATO could deploy initial equipment. American engineers recognized this disparity and attempted to address it through the assault float bridge system, a simplified version of the IRB using the same bay sections, but with reduced sophistication in connection mechanisms and control systems. The AFB was designed to be expendable, used for assault crossings where losses were expected, allowing the more expensive IRB sets to be preserved for operational level bridging, where they wouldn't be exposed to direct fire. The two-tier system balanced cost with capability, though it required engineer units to train on multiple bridge types rather than standardizing on a single system. The operational complexities of managing multiple bridge systems became apparent during WWII, when an American heavy division attempted to cross the Rhine using a combination of IRB, AFB, and older M26 bridge sections that were still in inventory. The mixing of equipment types created confusion about load capacities, connection compatibility, and assembly procedures. Engineers wasted nearly 2 hours at the crossing site, determining which bridge components were compatible and could be used together. The exercise controllers noted that this confusion would have been catastrophic in actual combat, where 2 hours of indecision at a river crossing would likely result in the entire division being destroyed by Soviet artillery and airstrikes. The lesson from Reforger 85 drove a complete revision of U.S. engineer doctrine finalized in 1986. The new doctrine mandated standardization on the IRB system as the primary tactical bridge for all operations. Older systems would be phased out over 5 years. Training would focus exclusively on IRB employment. Supply chains would be simplified to support a single bridge type. The standardization came at significant cost, requiring the replacement of bridge inventory that was functionally adequate but not compatible with the new standard. Congress approved the funding, recognizing that bridge compatibility wasn't optional if NATO expected to survive the first week of a European war. While NATO struggled with bridge standardization, Soviet forces were developing a system that would render much of the bridging debate irrelevant. Intelligence reports in 1986 described a new Soviet tank design that could cross rivers without any bridge at all. The T-80, entering service with elite Soviet units, included factory-installed deep wading equipment that allowed it to cross rivers up to 5 meters deep without external preparation. Previous Soviet tanks could be modified for deep wading, but the process required several hours of work by trained crews, installing snorkel tubes, sealing hatches, and waterproofing electrical systems. The T-80's integrated system could be activated in less than 30 minutes, making it tactically viable for units encountering unexpected river obstacles during rapid advances. The tank's crew remained fully protected inside sealed compartments, while the tank drove along the river bottom using its normal engine and tracks. NATO had no equivalent capability. American M1 Abrams tanks could ford rivers up to 1.2 meters deep, essentially large streams rather than actual rivers. Deeper water required bridges. The disparity meant Soviet armor could bypass defended bridge sites by simply crossing upstream or downstream at undefended points, forcing NATO to defend entire river lengths rather than specific crossing sites. The defensive burden increased exponentially. American armor designers studied the T-80's deep wading system and concluded it was technically feasible for the Abrams, but would require extensive redesign of the engine air intake system, exhaust routing, and crew compartment sealing. The estimated cost was $800,000 per tank for retrofit of existing vehicles, with modifications taking approximately 6 months per vehicle at depot-level facilities. Given that the Army operated over 7,000 Abrams tanks, full fleet modification would cost nearly $6 billion and take over 20 years with available depot capacity. The Army made the decision not to pursue deep wading modification. Instead, they would invest in bridge technology and accept that river crossings would remain engineer-intensive operations, requiring careful planning and extensive resources. The decision reflected American military culture's emphasis on technological solutions over tactical flexibility. Soviet forces accepted the tactical constraint that tanks needed, bridges, and developed doctrine around it. American forces preferred to maintain doctrinal flexibility and invest in bridge technology rather than constraining tank design. The investment materialized in the Enhanced Ribbon Bridge program, initiated in 1987, which aimed to increase IRB deployment speed through improved launching systems. The standard IRB deployment method required engineers to assemble bay sections on shore, then push the partially completed bridge into the river and continue adding sections until it reached the far bank. This shore-based assembly was slow, and exposed crews to enemy fire for extended periods. The enhanced program developed the bridge erection boat, specialized vessels that could carry IRB bay sections and assemble them while floating in midstream. Two BEBs working from opposite banks could meet in the middle, significantly reducing construction time. Testing at Fort Story in 1988 demonstrated a complete IRB bridge across a 200-meter river in 47 minutes using BEB deployment, compared to 90 minutes using shore-based assembly. But the BEB system introduced new vulnerabilities. The boats themselves were large, slow-moving, and lightly armored. They made excellent targets for enemy artillery and anti-tank guided missiles. Doctrine specified that BEBs would only be used when air superiority and counter-battery fire could suppress enemy engagement of the crossing site. In scenarios where NATO didn't control the air or couldn't effectively suppress Soviet artillery, BEBs would be too vulnerable to employ, and engineers would revert to slower shore-based assembly methods. The question of air superiority brought engineers into direct conflict with NATO air power doctrine. Air Force planners allocated fighter aircraft to counter Soviet air forces, strike deep targets in Warsaw Pact territory, and support ground operations in that priority order. Providing continuous air cover for river crossings was considered a low priority compared to strategic missions. Engineer commanders argued that undefended crossings would be destroyed, negating any advantage gained from deep strike operations. The doctrinal argument was never fully resolved before the Cold War's end. What did get resolved, through bureaucratic pressure and operational necessity, was the question of crossing site selection and preparation. NATO doctrine in the late 1980s established that engineer reconnaissance teams would pre-survey potential crossing sites throughout West Germany during peacetime, identifying locations with favorable bank conditions, good approach routes, and defensible bridgeheads. These sites would be catalogued, prioritized, and incorporated into war plans so that advancing units wouldn't encounter rivers as unexpected obstacles, but rather as planned phase lines with pre-positioned equipment and prepared approaches. The reconnaissance effort, conducted between 1987 and 1989, identified over 300 viable crossing sites along major rivers in West Germany's NATO defense sector. Each site received a detailed survey documenting water depth, current speed, bottom composition, bank height and stability, and approach route capacity. Engineer units conducted training exercises at these sites, rehearsing bridge deployment under conditions matching expected wartime scenarios. By 1989, NATO engineers had transformed rivers from unpredictable obstacles into planned operations, with known variables and rehearsed solutions. The irony was that all this preparation became obsolete before it was ever tested in combat. The fall of the Berlin Wall in November 1989, followed by the dissolution of the Warsaw Pact in 1991, meant that the scenarios NATO had spent 40 years preparing for would never occur. The bridges designed to carry 60-ton tanks across Central European rivers under Soviet artillery fire would instead be used for peacekeeping operations, disaster relief, and the occasional regional conflict where river crossings were necessary but rarely contested. The First Gulf War in 1991 provided the only significant combat test of Cold War bridging systems, and the results were instructive in unexpected ways. Coalition engineers built multiple IRB bridges across the Euphrates River to support the advance into Iraq. The bridges performed flawlessly in terms of load capacity and structural integrity. M1A1 Abrams tanks weighing 63 tons crossed without incident. British Challenger tanks crossed successfully despite exceeding design specifications. But the bridges revealed a weakness that had been deprioritized during Cold War development. Desert sand contaminated hydraulic systems, causing connection mechanisms to jam. The fine dust infiltrated bay section compartments, adding weight and reducing buoyancy. Seals designed for European water temperatures failed in the extreme heat of the Iraqi desert. Engineers spent as much time on maintenance and cleaning as they did on bridge operations. The lesson was that bridge systems optimized for Central European warfare weren't necessarily suitable for global deployment without modification. The U.S. Army responded with the modular bridging system, development of which began in 1992. intended to replace both the IRB and several other specialized bridge systems with a single modular design that could be configured for different environments and tactical situations. The MBS never achieved its goals. Budget cuts following the Cold War's end reduced funding. Operational deployments to Bosnia, Kosovo, and Afghanistan revealed that rapid tactical bridging was less important than sustained logistics infrastructure. Engineers found themselves building semi-permanent bridges that operated for months or years, rather than tactical bridges used for hours or days. The Cold War bridge problem, which had consumed billions of dollars and thousands of engineering hours, essentially solved itself through geopolitical change rather than technical innovation. The 60-ton tank bridge that NATO needed to fight the Soviets across the rivers of Central Europe became a solution in search of a problem once the Soviet threat disappeared. Modern bridge engineering has shifted focus from rapid deployment under fire to long-term sustainability in stability operations. Yet the legacy of Cold War bridge development remains embedded in military doctrine and equipment design. The IRB system, despite being designed for a war that never happened, continues to serve in U.S. Army engineer battalions. The principles of modular construction, rapid deployment, and traffic control developed during the Cold War inform current bridging operations. The institutional knowledge gained through decades of problem-solving, testing, and doctrinal development created an engineering culture that continues to influence how militaries approach obstacle crossing today. The engineers who designed these systems, who struggled with the physics of displacement and load distribution, who calculated current speeds and anchor cable angles, who developed doctrine for moving 60-ton vehicles across water, never saw their work tested in the scenario they prepared for. The great tank battle across the rivers of Central Europe never occurred. The Warsaw Pact never invaded. The bridges built to stop them were never needed for their intended purpose. But consider what those engineers accomplished despite that outcome. They took a problem that seemed unsolvable in 1950, when Captain James Thornton's Pershing nearly sank through a Bailey Bridge on the Chongchon River, and they solved it through 40 years of persistent innovation. They developed bridges that could carry tanks twice as heavy as World War II armor. They created deployment systems that reduced crossing times from days to hours. They established doctrine that balanced speed with safety, firepower with mobility, cost with capability. They did this knowing they might never use the equipment in combat. They did it because the alternative, failing to solve the problem, would have meant surrendering the tactical initiative to an adversary whose doctrine was built around exploiting NATO's bridging weaknesses. The engineers who worked on these systems weren't motivated by glory or recognition. They were motivated by the knowledge that if deterrence failed and war came to Europe, soldiers' lives would depend on whether bridges could carry the tanks that protected them. In that sense, the Cold War bridge problem was solved not through technical achievement alone, but through the deterrent effect of NATO's demonstrated capability. Soviet planners knew that NATO could move heavy armor across rivers efficiently. That knowledge influenced Soviet calculations about the probable outcome of any invasion. The bridges that were never used in combat may have prevented the war that would have required using them. The story of Cold War bridge development is ultimately about the unglamorous work of military engineering. The thousands of engineers who spent careers calculating load capacities and testing deployment systems, who conducted exercises in rain and darkness, who revised doctrine after every lesson learned, who built training facilities and taught soldiers to assemble bridges under stress. These engineers didn't storm beaches or capture objectives. They solved physics problems that enabled others to do those things. Captain James Thornton, whose Pershing tank crossed the Chongchon River in 1950 on a bridge that was barely adequate, retired from the army in 1972. He spent his final years watching the development of bridging systems that could have saved his crew from the terror of crossing on failing pontoons while under fire. He attended engineering conferences occasionally, speaking about the importance of mobility in armored warfare and the critical role engineers played in enabling that mobility. Thornton died in 1993, 2 years after the Soviet Union collapsed. He never saw the IRB system used in major combat. He never witnessed the river crossings that engineers had prepared for decades to execute. But he understood something that many outside the engineering community missed. The purpose of military engineering wasn't always to be used. Sometimes the purpose was simply to be ready, to be capable, to demonstrate to potential adversaries that the obstacle they planned to exploit had been overcome. The bridges designed to carry 60-ton tanks across European rivers represented that readiness. They embodied NATO's commitment to solving whatever problems the Soviet threat presented. They demonstrated that Western engineering could match or exceed Warsaw Pact capabilities despite fundamental differences in doctrine and philosophy. Most importantly, they provided options to military commanders who needed to know they could maneuver forces without being constrained by rivers that enemies thought would protect them. Today, many of those Cold War bridge systems remain in use, adapted for different purposes than their designers intended. IRB sections support disaster relief operations, enabling heavy equipment to reach areas isolated by floods or earthquakes. Military engineers deploy portable bridges in developing nations as part of humanitarian missions, building infrastructure that serves civilian populations. The technology developed to wage mechanized warfare across Central Europe now helps build schools, deliver medical supplies, and connect communities. The engineers who built these systems might find that outcome fitting. Engineering has always been about solving problems, about making difficult things possible, about enabling people to cross obstacles that initially seemed insurmountable. Whether the obstacle is a hostile river under enemy fire or a geography that isolates communities from essential services, the engineering principles remain the same. Calculate the loads, understand the forces, design the structure, test it thoroughly, and build it well enough that lives depending on it are protected. The 60-ton tank bridge was designed for a war that thankfully never came, but the engineering knowledge gained in developing it continues serving purposes the original designers never imagined. That, perhaps, is the true legacy of Cold War military engineering, not the weapons systems or the tactical capabilities, but the accumulated knowledge of how to solve difficult problems under pressure, how to balance competing requirements, and how to build things that work when failure means lives lost. The next time you see a military engineer unit deploying a bridge, whether in combat footage or disaster relief operations, remember that their equipment and doctrine represent decades of innovation, driven by a problem that seemed impossible to solve. Heavy tanks needed to cross rivers quickly. Physics said it couldn't be done within practical constraints. Engineers spent 40 years proving physics wrong, or at least proving that creative engineering could find solutions within the constraints physics imposed. They succeeded. The bridges carry the weight, the tanks cross the rivers, and the engineers, anonymous specialists whose work rarely makes headlines, continue doing what they've always done, making the impossible merely difficult, and the difficult routine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.